Okay, so now we're going to look at examples of the Bregman divergence. Okay, so the simplest example is the Euclidean divergence. Okay, so as you might expect, it's like that corresponds to the convex function, which is just given by the Euclidean distance. All right, so you can check that for this convex function, which is just 1/2 the sum of squares, right? The divergence between 2 points in Euclidean space is just given by 1/2 this Euclidean distance squared, right? So this is just 1/2 of the square Euclidean distance. So it's not very exciting, but yeah, that's what it is. So let's look at another example, which is the logarithmic distance. Logarithmic divergence. Okay, so the convex function here is just negative sum from I equals 1 to n of the log of ci. Okay, so this is on the manifold of positive measures. Okay, so you can check what its gradient is. Gradient is just equal to negative well, this is you should think of this as a vector, right? Okay, so this is just the ith component of that vector. Okay, so the Bregman divergence then is just equal to the sum from I equals 1 to n of the log of ci prime over ci plus ci divided by ci prime minus 1. Okay. All right, so that's one possibility. And then there's another convex function you can consider, which will lead to the KL divergence. So for the negative entropy, right, the Bregman divergence is the same as the KL divergence. Okay. So it's the sum cos ci log cos ci divided by cos ci prime minus cos ci plus cos ci prime. Okay, and then when the sum of cos ci equals the sum of cos ci prime equals 1, this is the Bregman divergence. It's like for probability vectors, right? So this is the KL divergence for probability vectors. Okay. All right, and then if you recall, it's like encoded. It's like in any divergence function is a Riemannian metric, right? So in the context of KL, it's like the underlying the take-home message is that KL divergence is Bregman divergence, which comes from a convex function. That convex function is the negative Shannon entropy. And then the metric, it's like which this Bregman divergence or this KL divergence is like encodes, is the Fisher-Rao metric. Okay, all right. Anyhow, alrighty. So that's some nice connections. It's like between many interesting objects in statistics and information theory. Okay, so let's look at one more example, which is the free energy of the exponential family. Okay, so we want to, if you recall, it's like in this exponential family, there was a normalizing factor, psi of theta, right? So in the exponential family, there is a normalizing factor. And the normalizing factor, as the name implies, it's like ensures that it actually is a probability distribution. Okay, so let's recall what that normalizing factor is, right? Right. So if you recall, it's like that's also referred to as the free energy in statistical physics, or the cumulant generating function in statistics. Okay, all right. So so what we want to do is to essentially construct the gradient, right, of this normalizing factor, because that's how you construct this hyperplane. It's like at a point, and then use that to construct the Bregman divergence associated with that convex function. Okay, so so we want to compute the associated Bregman divergence. So what I'm going to do is I'm going to use this condition which defines, it's like this factor, which is the normalization condition. Okay. Then so that involves integrating, it's like the exponential family. Right, and if you recall, it's like this term is defined here, guarantees that the integral of that is 1, right? Okay, so this condition is equivalent to this condition, basically. Okay, so I can differentiate this with respect to theta, theta I. And what happens then is I get the integral of xi minus dd theta I phi theta p x theta dx. Right, because essentially what's happening is that when I differentiate this thing with respect to theta, I get the derivative of the thing inside the parentheses. It's like times this exponential again, and this exponential is just the probability distribution. So that's where I get this, right? And but differentiating with respect to theta of this is equal to 0 because when 1 is independent of the theta i's, right? So that partial derivative of that respect to theta I is 0. So that's one condition. Okay, so from that we can conclude the following. Okay, so let's see what happens. Okay. All right, so this means that d theta I phi theta is equal to the integral of xi p. Right, I just broke this integral up into two pieces, right? So all right, so this term is just depends on theta, right? But I'm integrating with respect to x, so I can take that factor out, right? And then integral of px comma theta is 1, so this is why the piece associated this times this integrated is just the thing inside the parentheses. And then the other piece is this thing here. All right, and that's obviously just the expectation of xi. Or sort of xi bar. Okay, so that's telling you that the gradient of this sort of normalization factor is just the expectation of the vector x. Okay. And then you can check that the Hessian of this is the covariance matrix. Which is positive definite. So, so that function is convex. Okay, then with that, you can construct the Bregman divergence, right? Right, so it's just defined by this, more generally speaking, right? So this is just the general definition, it's like of the Bregman divergence. And then you can show after a bit of work that this is really just the KL divergence applied to the exponential family. domain can show this is the KL divergence. Okay, between two probability distributions. And it requires, it's like a little bit of careful calculation. It's like, but you know, the bottom line again is that this recovers the KL divergence for the exponential family. Okay, so let me just stop here for now. And second, the next thing we'll talk about is the issue of the Legendre transform. And one of the things you'll find is that the idea of Legendre transforms in duality is like show up again and again in the theory of information geometry. Okay, and then your first flavor of this again is in the Legendre transform. So let me just stop here for now.